All right, lesson 2.11, logarithmic functions. So we're going to understand the domain of a log function in general form is any real number greater than 0, and the range is all real numbers. We're going to identify key characteristics of log functions and transformations. We're going to determine whether log functions are increasing, decreasing, concave up, or concave down. We're going to tell that log functions do not have extrema except on a closed interval, and their graphs do not have inflection points. And we're going to analyze and use limit notation for end behavior. All right, in this lesson, our goal is to summarize the key characteristics or logarithm functions before moving into properties of logarithms, solving logarithmic and exponential equations, and modeling with real-world applications. So the domain of a log function says we have shown that the log function y equals log base b of x is the inverse of the exponential function y equals b to the x. That is, if f of x is equal to b to the x, then the inverse of f of x is equal to log base b of x. From our last lesson on inverses of exponential functions, for a function f and its inverse, the inverse of f, we have shown that the domain of the inverse is equal to the range of the function, and the range of the inverse is equal to the domain of the function. So let's summarize those findings here. So some properties of the graph of a log function that we've seen so far. It says the graph of a log function in the form of f of x equals log base b of x. It's going to have an x-intercept at 1, 0, and there is no y-intercept. The y-axis, or x equals 0, is your vertical asymptote of the graph. If your base is greater than 1, the function will be increasing. If your base is between 0 and 1, the function is decreasing. The graph of f contains the points 1, 0, b, 1, and 1 over b, negative 1. The graph is smooth and continuous. It has no sharp corners or gaps. All right, so let's find the domain of each log function. So, well, for one thing, our parent function is y equals log base b of x. Remember we said it's got that vertical asymptote at x equals 0, and it keeps going to the right. So we know that its domain is x is greater than 0, okay? Your x is right here. So the domain is going to be that piece set greater than 0. Now some of them we'll have to think a little bit about, but in general, that's how we can find it. So let's look at A. A says f of x equals log base 2 of x plus 5. So we know that this x piece right here has to be greater than 0. So we subtract the 5, and so we get x is greater than negative 5. So we know that our domain is going to be negative 5, not included, to infinity. Now for B, we're going to have to think a little bit on. But first, it starts out the same way. We know that this has got to be greater than 0. So 1 minus x over 1 plus x has to be greater than 0. Well, what kind of numbers are greater than 0? Positive numbers. So that means that this fraction is going to have to be positive. How can I get positive when I'm dealing with a fraction? Well, first thing, if I have a positive over a positive, that's positive. Or I could have a negative over a negative because that'll make it positive as well. So I have to look at two different scenarios here and see which one would be true. All right, so let's start out with the negative over the negative. So that means at the top, the 1 minus x would have to be negative, which means it has to be less than 0. And the denominator, the 1 plus x, also has to be negative, so it has to be less than 0. So we're going to solve both of these. Oops, it's negative x. And remember, when you divide by negative, you flip your inequality sign. All right. Both of these has to be true. So it's going to be where both of them are true at. If you think about a number line, if you graph where x is greater than 1, you're graphing all of that. And if you graph where x is less than 1, you're graphing all of that. There's nowhere there that makes them both true. So therefore, we can't not make this a negative over a negative. So that didn't help us with domain. It just eliminated that that's not going to work. So then let's think about the positive over a positive, which means the numerator has to be positive, so it's going to be greater than 0. And the denominator also has to be positive, so it's going to be greater than 0. So I'm going to solve both of these. Oops. Don't forget to change your sign. You divide by negative. All right, solve this one. And so if we think about a number line on this, has to be less than, that's a negative 1. Has to be less than 1, so that would go this way. Has to be greater than negative 1, so that would go this way. And so it overlaps in between the two there. That's what makes both of them true. So then that gives me my domain. So I know, I'm going to write it, I'm changing colors here. Let's go with the red. So we know that our domain, the first one didn't work out. But we know from this one, our domain then is going to be between negative 1 and 1, and both of them have parentheses. All right, on C. C has absolute value. So we know that this piece here is going to have to be greater than 0. Well, when is absolute value greater than 0? It's always greater than 0. So we're just going to take and we're going to split this. Remember, with absolute value, what's inside can be positive, and it'll be greater than 0. And what's inside could also be negative. All right, so if I work this out, I get x is greater than 2. And so I get x is less than 2. And so if you think about a number line, let me erase part of that previous problem there so I have room. If you think about on a number line here, looking where x is greater than 2, where x is less than 2, this one could be either one of them, because you're looking for where it's greater than 0. So the only place that there is not included on both of them is at 2, because at 2, that absolute value would actually equal 0, and it has to be greater than 0. So my domain then, is going to be from negative infinity to 2, union 2 to infinity. All right, so just so we can see our answers there. Those were our 3 domains. All right, example 2 says the graph of a log function is given. Match each graph, A through D, to one of the following. So we got log base 2 of x, log base 2 of negative x, negative log base 2 of x, and log 1/2 of negative x. Excuse me. So I would start out with the first one there, log base 2 of x. So if I look here, that's our normal log function. There's no transformation. It's just a parent log. That is answer choice C. Whoops. Sorry, different program, didn't turn the pen on. All right, so this one right here is our normal parent looking function. Has the x-intercept at 1, 0. It's got the vertical asymptote at x equals 0. It's increasing because my base is greater than 1. So this is going to be C. And I'm going to put here that this one is f of x. All right, then if I have log base 2 of negative x, that's literally taking graph C and reflecting it across the y-axis, because that's what that negative is going to do. So when I look on here, which one looks like C but reflected across the y-axis? That's going to be A. And so this one is my g of x. Now, h of x there says it's not negative log base 2 of x. So again, look at graph C. That negative is just going to make it reflect across the x-axis. Which one of the remaining 2 is reflected across the x-axis from C? That would be B. And so this one would be h of x. And so by default, D has to be our k of x. The reason is because the negative x, remember, makes it reflect across the y-axis. So without that, it would look like this. And its base is between 0 and 1, which means it's decreasing instead of increasing. That's why it appears to be upside down from what we're used to seeing, but it's because your base is between 0 and 1. All right, so based on your findings, which graph above would also be correct for y equals log of 1/2 x. And so the 1/2, log base 1/2 of x, that would also be graph B. Because we just drew the 1/2 of x right there. So that would be graph B. Okay, and if you want to make note, it's your base is between 0 and 1, so it is decreasing. And that's why it's going to be graph B. All right, example 3. So sketch the graph of the parent function. F of x equals log base 2 of x. So remember, log base 2 of x is the same as 2 to the y equals x. And so once it's to complete the table below, but they gave us the x values. So when I go through here, I'm thinking 2 to what gives me 1? Then 2 to what gives me 2? 2 to what would give me 4? And 2 to what number would give me 8? Remember, this is a log function that has no transformation. So we know there's that vertical asymptote at x equals 0. All right, then how is the graph of g of x equals negative log base 2 of x translated from f of x? So what they're saying is, what is that negative going to make happen? We know that's going to be a reflection across the x-axis. All right, make a table of values for g of x, graph g of x on the grid above. So using this, we know if we had xy, then it's just going to become x negative y. Okay, so my x's are going to stay the same, and my y's are all going to change sign. And then graph that. So my asymptote's still the same. It didn't change. It was an x equals, and all we did is change the y's. And then it says analyze both f of x and g of x, including domain, range, increasing, decreasing, concavity, intercepts, and asymptote. All right, so for f of x, let's see, we know our domain is negative infinity. I'm sorry, it's not negative infinity to infinity. It starts at 0 and it goes to infinity. Our range is negative infinity to infinity. Increasing or decreasing, we can see it's increasing at a decreasing rate. Concavity, it's concave down. Intercepts. We have an x-intercept at 1, 0. There is no y-intercept. And your asymptote, your vertical asymptote at x equals 0. All right, for g of x, our domain is the same, 0 to infinity. Range is the same, -infinity to infinity. Our graph here is decreasing at an increasing rate. It's concave up. We have an x-intercept at 1, 0. And our vertical asymptote is also at x equals 0. Now let's talk about that concavity on this one, because I don't know if recently we've seen decreasing at an increasing rate. So, looking at my blue graph, I can see that I'm decreasing. But as I go along this graph, my slope is getting more towards 0, okay? So it's increasing. It's not as negative as the previous time. So that's why it's decreasing, because we're still going down, but it's at an increasing rate because we're getting closer and closer to becoming positive each time we go around. All right, example 4. So it's given the function, determine the asymptotes and the end behaviors using limit notation. All right, so we know that our parent function for log has a vertical asymptote at x equals 0. And so if I look at a, it's now at y equals log of x minus 1. That minus 1 tells me that everything is being moved to the right one, including that vertical asymptote. So my vertical asymptote is now going to be at x equals 1. So then my limit, as I go to the left, so as x approaches 1 from the left, I'm just going to put y, because that's what they named it, is going to be going down to -infinity. And then the right hand says the limit, as x goes towards infinity, y is going to go up to infinity. Because we know that this graph didn't change, except for it literally got moved to the right. Now I'm going to jump down and do D. Because D says my graph is just moving down 3. So if you think about it being graphed, you're just going to move it down 3. So now it's doing this. So my vertical asymptote isn't going to move. It's still at x equals 0. And so our limit as x approaches 0. Oops, this should have been from the right. As x approaches 0 from the right, y is going to go up to infinity. And the limit as x approaches infinity, hold on, whoopsie. When I put that plus, I'm thinking the other side. All right, so as the limit as x approaches 0, so this side of my graph, we're going to go down to -infinity. As x approaches positive infinity, that's over here, my function is going to keep going up to positive infinity. Now C combines like A and D. So C says, first this is the same thing as saying negative log of x plus 4 and then a plus 2. So it's got a lot of different stuff going on there, okay? So it's got, well, my answer key is different than, all right, so your problem, I'm sorry, it says a plus here. So let's go with yours. All right, so here we're just showing that our graph's going to move to the left 4 and it's going to go up 2. So if I move to the left 4 and up 2, my graph's going to look something like this, where I have that asymptote at -4. So my vertical asymptote went to the left 4, so it's at -4. So the limit as x approaches -4 from the right side, because we're coming in from the right, our y is going to be going down to -infinity. And then the limit as x approaches infinity, y is going to keep going up on this side, so it goes up to infinity. Then B, remember this is the same thing as saying log of negative x plus 2, which is the same thing as log of negative x minus 2. All right, so we know that means we're going to reflect across the y-axis, and then we're going to go to the right too. So that vertical asymptote, the reflection across the y-axis doesn't affect it because it's already on the y-axis, but then it's going to go to the right too. So my vertical asymptote is going to be at 2. Now my graph originally looks like all these others, but we reflected across that y-axis, so now my graph is going to go the other direction, so it's going to look like this. So when I do my limit, as x approaches negative infinity, the y value is going to go up to infinity. And then the limit as x approaches positive 2 from the left, because my graph's all on the left side of it now, the y value is going to go down to negative infinity. All right, example 5 says use the table of values below to determine whether a function is increasing or decreasing and the concavity of the function. Make a sketch. Can you determine the domain of the function? All right, so we can see here that our graph is increasing. I can tell that because my y values are getting bigger. We can see that they're increasing at a decreasing rate because between negative 2.86 and 0, we increase by 2.86. Then we increase by 1, and then $1.86. So I'm increasing, I'm going to write it above it. So I increased by 2.86, 1, and 1.86. So we can see that rate of increase is getting smaller. So we're increasing, but at a decreasing rate. That might be one of our best examples to see how that works. So we're increasing at a decreasing rate. And so if we want to know concavity, then that's the definition of concave down. Make a sketch, and can you determine the domain? So if we do our sketch here, and so with it being at 1.01, that's telling me that we'll probably have that vertical asymptote there at 1. And so our domain is going to be 1 to infinity. Now when we look at B, we can see that our graph is decreasing because my y's are getting smaller. But when we look at the rate, this is decreasing by 2.10. Then we're decreasing by negative 1, by negative 1. And then we're decreasing by negative 3.66. No. What's wrong with my math here? I'm having trouble with the negative numbers. Tell you what, let's graph it and look at it. I don't know why I'm having trouble with the negative numbers. All right, negative 1.9. Oh, I know why. Well, all right. Anyways, negative 1.9, 2.10, negative 10, 1, negative 1, 7, negative 2. All right, so we can graph it like this. So we can see we are decreasing, and it's going to be, and our slope of it is actually increasing. So we're decreasing at an increasing rate. Which means we are concave up. And our domain looks like it's going to go from negative 2 to infinity, using the x values there to guesstimate it. So, and what I was doing wrong there when I was doing it is because right here it's such a large gap that this number was bigger, but it's over such a large space that it's not, the increments aren't as great. So we just have to be careful on that. And I didn't catch that. All right, example 6, application. Woohoo! Says a principal P invested at 6.25% is compounded continuously and increases to an amount K times original principal after T years, where T is equal to the natural log of K divided by 0.0625. Complete the table and determine how long it'll take before your investment doubles. All right, so we've got an equation there, so we're just going to plug in our K into our calculator and solve it, okay? Or you could put that equation into your Y equals and go to your table and find when K is 1, 2, 4, 6, 8, and 10, what that T value would be. And these boxes are too small for me. All right, when I want it to double though, I'm looking for when K is 2. Because it says that K, the amount K times the original price, so I want K to be 2. So look in my table, right here K is 2, and so I know it's going to be about 11.09 years. And use a graphing utility to graph the function. So just plotting those points. There's my graph. C says suppose you had $1,000 to invest. Your function for the amount in the account at any time would be A of T is equals 1,000 e to the 0.0625 t. Use this function to verify your answer in part A. All right, so we said in part A, remember, for it to double, it was going to take 11.09 years. So I'm going to go ahead and plug in that 11.09, and I should get twice as much as what we started with. Well, remember, on this one, we're starting with $1,000. And I'm plugging in 11.09 for my T. And so I just typed this in my calculator, and when I did it, I got $1,999.96. And so that is almost double. So by saying that it was approximately or about 11.09 years, we were pretty close. We're 4 cents off. All right, and that is the end of lesson 11.